Robert Metzger is the PMC chair of Apache Flink. In this part 2 of our 2-part introduction to Flink, Robert's going to talk about what it's like to use Flink as a developer. What are the APIs that we use to deal with this thing? He's definitely the right guy to learn this stuff from, so let's listen in. Hello and welcome to another episode of the Real-Time Analytics Podcast. I am yet again your host, Tim Berglund, coming to you from the StarTree studios, and I am delighted to be joined again by Apache Flink PMC chair and Decodable staff software engineer, Robert Metzger. Robert, welcome back.
Thank you. I'm really excited to be here.
We talked last week about Flink, and it was really just an introduction. Like, if you didn't know a lot about Flink, what Flink was, the idea was, let's make sure everybody does. We kind of talked about how it's put together architecturally, how it runs, and some of its basic sensibilities. And I enjoyed that discussion because I've always thought Flink approaches the world in kind of a unique way. And, it's one thing to study the parts and learn how to use it and everything, but you kind of need to listen to its view of the world. And that's why I was glad to have that conversation. This week, I want to talk about how to use it. So not the parts, not how to deploy it, but APIs. And there's kind of this 3-layered API system to Flink. Let us start at the bottom and walk up that stack. So yeah, let's dive in.
Yeah, so I think there's like a spectrum of APIs in Flink, a spectrum between really expressive APIs and easy to use APIs. And on the expressive spectrum, there is the let's say DataStream API and the process function. And this exposes you to the basic building blocks of Apache Flink, which is real-time events, state, and event time. So if you're using the process function in the Flink API, it gives you basically a Java interface to implement, and it exposes you to everything that makes Flink that are the basic ingredients that Flink uses for everything it exposes. So it allows you to process records for a tuple at a time. You can emit as many records as you want downstream to one or multiple streams. You can access state, like you can access terabytes of data with a simple function call that is delegated to a state backend. And you can access time or event time. Like you can access wall clock time or the time when the event has occurred in the real world. Like when you're doing historical reprocessing of data, it will show you the time when the event has occurred in the real world.
Yeah. And that process function layer is kind of like the lowest level of abstraction, right? I mean,
yes,
you implement a method, and the method gets called, and here's your event, and here's your state, and here's
Yeah, so it's really the basic primitives of Flink. If you want to go a level up, if you want to use let's say the window operators of Flink, they will all use these basic APIs. But if you don't want to go so deep, you can also use higher level abstractions. You can use the windowing API of Flink, where you can just say group all the incoming data into windows of 5 minutes and have them overlap for 1 minute, or create session windows for me. And this is how I want to handle events that arrive late and all that kind of stuff. Or if you want to do complex event processing, CEP, we have a library for that in Flink. This library is as well using all these basic building blocks that Flink exposes. And then there's a third thing in Flink. It's called the async IO operator that allows you to do interleaved calls to external services like a Redis or an API or whatever to look up data. Yeah.
Okay. Yeah. Because that's a problem when you've got a stream processing API, which is, I think, from a developer standpoint, fundamentally an asynchronous thing, right? Let's go to the lowest level, the process function. I have a method that gets called, and here's a event. Mm-hmm. It just runs, right? And if I need to do some synchronous operation inside there to go look something up to enrich the event and then emit it, that's kind of a bummer, right? You don't want to
Yeah.
be waiting around on a response. So that async thing is to manage that.
Yeah, you're effectively reducing your throughput to the throughput of this external service. So
Yes.
if you have to wait for 10 seconds per API call, you have to wait 10 seconds for every record to process, which is insane for like a real-time system.
Yes. And yeah, you're not, because you can't do things out of order. You can't just like have a bunch of threads waiting and have them come back. It's
Yeah.
got it. Can you? I don't know if this is too much without a whiteboard. Can you dive into how that async thing works a little bit? That's interesting.
I actually not. So I haven't really used it myself.
As I asked it, like I kind of
So-
probably need to draw this. So we don't have to do that. Yeah.
Yeah. So I think the basic idea is that it gives you a framework that allows you to issue requests to an external service, and then Flink keeps track of all the pending requests. And whenever a request completes, it will basically know that this request is good and send the result down. And this will be integrated with the checkpointing mechanism of Flink. So
Of course.
if your system is crashing and you're recovering, then Flink knows which records have pending requests from its state. So it will reissue these requests to the external system and then continue from there to guarantee that you don't have data loss.
Got it. Okay. And my guess is, in terms of the implementation, this is without some gigantic and resource hungry thread pool, but in the cool async.
So
way
I think exactly you need like the library that you're using to make these calls. They need to support futures and stuff. So you cannot just have an insane amount of threads lingering around. Yes,
because it's been a while since that's how we did that kind of thing. So
yeah.
Okay, so back to, sorry, interesting sidebar there. Back to, you've got process function, that's this low level API. To help me, how is a event modeled? What is the interface of the thing that I get?
Yeah, that's an interesting question. It can be whatever you want. So Flink supports POJOs, like plain old Java objects, for your data. So you can just create a Java, if you're using a newer Java version record, with all your fields, and then you use some JSON serializer and your basic or deserializer, and you're taking some input data and you're just mapping the data into your POJO, and then you can do the processing on these records. Flink also provides built-in types called the tuple type. So you can do like a tuple 5 or tuple 10 or whatever. And then you can just specify with the generics what types you want to have for the individual tuple fields.
What kinds of things are there?
Yes. And Flink has a pretty sophisticated serialization framework for this. So we have a special POJO serializer if you're using POJOs, and also special tuple serializer if you're using tuples, which is pretty efficient because we only deserialize in some modes of Flink. We only deserialize this part of your data that you're actually looking at. So we save some CPU cost there, and we use cryo as a fallback if you're using a data type that we cannot handle. Like if you're using some Java collection type, for example, in your tuple or in your POJO, then we fall back to cryo for serializing these types, which is less efficient.
Sure. It is astounding how difficult a problem serialization really is. It's conceptually very simple, but I imagine if we were to follow the history of the commits over the last decade or so, there's been a fair amount of work there.
Yeah, and in my experience, it's a big source for performance issues because you underestimate how much time you spend in just serializing and deserializing data. So in particular, since Flink has the this concept of state, we also need to serialize the state if you're writing the state to rocksdb, because rocksdb is implemented in C or C++, and we always need to serialize and deserialize the data out of Java into this rocksdb library. So every access to the state is expensive. I mean, CPU intense.
Yeah. Should do an episode sometime on the carbon footprint of JSON.
Not good. Yes.
Yeah, it's significant. Okay, so process function and layer on top of that gives you, and I guess, what are reasons that you'd want to live in the bottom layer there? Because I know you said you have access to state, you have access to the event, and kind of all of the Flink machinery is yours, but it's not particularly expressive. It's extremely flexible, but not very expressive. It's kind of like assembly language stream processing. So what pushes one down into that layer if one is not a Flink committer building a higher layer?
I think hardcore performance critical use cases are pushing you down into this. There's a lot of companies that earn money with ads. And when you're doing ads, we know we have Flink users that are using Flink for ad attribution. So you're doing basically a big join between the information why somebody has seen an ad and when somebody clicks an ad. So if you're going to Reddit and Reddit decides that based on your geography and your browsing history and whatever, they decide to show you a certain ad. And they store this information about deciding who to show which ad in some system. And then there's another system that tracks when somebody clicks on ads. And to track how effective their algorithm is, they want to join these two streams of events, like the showing which ads to show and which ads were clicked. And this is a pretty expensive join if you consider the amount of ad impressions and all that you have. And for that, you can use the process function, because you could use this as a cache where you store all the ads that you've shown for the last, let's say, 24 hours, and you join it with the ad click stream. But for ad events that were older than 1 day, you want to do a lookup in the database or a lookup in some external system. So let's say it's a highly customized join that has some part of the join in local state, but it has the option to execute custom code to go to another system and look up really old data. Gotcha. And for this use case, you could also use the join thing in Flink, but that wouldn't be efficient if you want to be able to join data up to, I don't know, like 1 week or so.
Sure. You're creating storage tiers there, and you're kind of doing that programmatically. I've got the archival data here, and the hot set is here.
And another option would be if you're doing some kind of window operation where you're collecting data for 1 hour, and now there is some users that sometimes have really late data because, for example, the data is on a mobile phone and they were on a flight, and then data arrives like five hours late, but we know it belongs to this particular window. And then what you could do is you could implement custom code to basically fix the data from this window operator. So you go into your database or wherever you store your final result and change the aggregations a little bit and say, look, we actually had 2 more customers in this particular hour. They were just on a flight during this time.
Got it. So I've got an instantaneous report of whatever that window tells me, and then updates trickle in, and it gets a little more accurate over time. But that's something I'd need to do at the process function layer. Okay, take us up a layer. We have things like join and map and like what this now suddenly I've got abstractions that are streams, and I can do things to them. So
process function is also an operator. So everything is glued together by the DataStream API. The DataStream API is where you can define the sources and sinks and all the operators. And one of the operators is the process function, or is a window operator, or a CEP operator. So, and also a table API. So you can also use the DataStream API to connect process function with Flink SQL. That's possible. You can, in the same Java code, use both of these APIs together.
Oh, nice. Okay, that I did not know. So and I guess the listeners probably know this. I don't know that much about Flink. I've never used it in Anger, so I am 100% learning things today. So, okay, now the so we I guess conceptually are going a layer up, but these are all data stream operators on streams. That's fundamentally the
Yes.
the programming model for Flink.
Yeah.
It's just summarizing here. Most of it strikes me that in common stream processing use cases, you either just want to write SQL or you want an API that gives you fairly high level abstractions to work with. What do you actually see in terms of? And I don't know what kind of data you have, but just like from your sense of how people talk about things and what people use and where the questions are, where is most of the action in the API? What do most people use?
Yeah, I think the, let's say, normal DataStream API and like map operations, filter operations, and process function. So if process function might sound scary, but it's actually often used by advanced users, or like medium to advanced users. So it's not as complicated as it might sound. You don't have to use all the ingredients that it's exposing. And the other half of the users, or let's say the users that are using Flink SQL is growing. So that there's clearly a trend that more people are using SQL.
Got it. How about if you want to do stateful things? Does that, I mean, I know you've got access to the state store, but a stateful thing like a group, an aggregation, a join, are those easy to do in the process function, or do we want to use higher level parts of the API?
So I think when people are starting out with Flink, they of course use the existing operators like join operators, window operators, and so on. And as they progress, as they learn how Flink behaves under certain load patterns in their environment and so on, they start optimizing, and they might start to replace an existing operator that Flink provides with a custom operator built with process function. So that is
Got it.
yeah, and it of course depends if you, like, there's companies that have like one or two really big use cases that are extremely important to them, and then there's companies, for example Uber, they have built a Flink SQL platform. They have, I don't know, a lot of use cases around Flink, and most of these use cases are in SQL. So it's really a wide spectrum of how people are using the system.
Good. Okay, I want to get to Flink SQL, but before we get there, the table operator. What does it mean to turn a stream into a table? How does it work?
So the table API is like table API and Flink SQL are basically the same.
Oh,
So
okay.
table API is going through the same optimization steps as Flink SQL. So they, like, table API is just another interface. So instead of writing text to express your streaming application, you're writing Java code to express your streaming application. But still, it's providing you with, like, table API is providing you with fairly high level abstractions. Like, it's
Gotcha.
taking care of it. So when in table API you're defining some projection and some filter and then some aggregation, the optimizer of table API is free to rearrange where it's actually doing this filtering or where it's doing the projection, because it goes through the same optimizer that Flink also uses for SQL. If you're using the DataStream API, on the other hand, there's no optimization in between. So if you're doing something inefficient, that's your problem.
That's your problem. Exactly. You should try harder.
Yeah.
You mentioned in the last episode, you gave a little bit of historical context about the origins of Flink.
Mhm.
And you said it was kind of a response to early Hadoop. which seemed to have thrown out decades of database research and lessons learned. And you just described one. So being able to optimize the order in which things happen in the way a query is written is a fundamental part of any sort of practical, commercial, useful database, any kind of database that anybody would actually use in a running system. So there you go.
Even though I think for a streaming system, what you want is a iterative optimizer. So you want an optimizer that like you're starting your streaming application and it observes the pattern, like how much data is coming over which stream and what's selectivity and so on. And then at some point you're basically auto scaling, and the optimizer is giving you information. The optimizer is using the information it has collected to incrementally optimize your streaming application. Because with a batch SQL engine, you have all the information. Ideally, you have a lot of information already. Like you know the size of your input tables, and you might know the selectivity of some predicates and so on. In a streaming system, this is harder because you have infinite sources. So you have to assume infinite data. So you cannot do stuff like rearranging a join in a SQL in a streaming system, because there's no small and no big input to read as you have in a batch system.
Right. And in a traditional relational database, you have probably gathered some statistics about the data. So things like selectivity of predicates, you'd be able to make predictions about that based on what you actually know about what's in the data.
Yeah.
So yeah, good point. Okay, so that's like you could think of it as just-in-time optimization. That's iterative, and continuous.
Yeah.
Right. Nice.
I mean, Flink doesn't have that, but if people are interested, it's an interesting topic.
You're open to pull requests. If somebody wants to add a gigantic new, person years long PR, that would be fine. Please rebase into one commit. Actually, I assume you don't want that. But top of the stack, Flink SQL. Streams aren't tables, right? And SQL is designed for tables, and this is a thing that the various streaming systems do. But just give us a top level overview. You said it's growing in popularity. How's it work? Give us a quick summary of Flink SQL.
So the idea of Flink SQL is really to give a broader audience access to stream processing, not just to distributed systems experts that know how to optimize a streaming pipeline, but to people that know how the data looks like and what they want to do with it. And basically in a streaming SQL application, instead of tables, you're working with streams. And that's about it. And then you can do the same things basically. So you have to bend a little bit your mind when you're starting to use Flink SQL. But in principle, once you got the idea, it's not terribly hard. Like if you start from a simple use case where you just where you have a stream of events and you want to filter out, let's say, all users that are older than 30. That's just a select star from, or let's say insert into blah, 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 select star from where age below 30. And that's it. So that's a simple transformation.
We call that the Logan's run query. But yeah, and a simple stateless query with the output, it's easy to wrap your mind around how that works, right? If you don't know streaming SQL, it's not hard to think about. How about if I want to do an aggregation where the output of that, even if the input is a stream, the output's a table? How does that work?
So you can, let's say you want to do a running aggregation. So you just want to,
if we're thinking of
average age,
average age of the people inside this big domed city. There's a film I'm referring to, a dystopian sci-fi film from 50 years ago. You want to compute the average age of all the citizens in this city. People are born and are dying, and so it's just that's all there is. Yeah.
So let's say you want to have the average age per city. So you group by city, and you say select average age, average age, average age, comma city. So your input is a stream of cities and ages, and probably some more data, and your output is a let's say change stream. So whenever a new record comes in, Flink emits an update event. So if city A has 15 people, and then there's another person coming, and it's 16 people, then Flink will emit an update event that says change the count from 15 to 16.
It's like change data capture on the table, like the output of a CDC process on that table.
Exactly. So it doesn't have to be. It can. So you can also use CDC input for Flink, and Flink generates CDC output as well. Like both is possible. Like you can join. Let's say you have two tables in Postgres, and you want to do a join between these two tables. You can basically you create a CDC stream for both tables into Flink. Then you do your join in Flink, and the result is again a CDC stream of this join result. So whenever something updates in one of the input tables, the resulting CDC change stream contains an event that reflects this change in the join result. And then you can write this CDC stream to a database, and again, you have a table.
And is that if I want to query, so I'm computing the average age of cities from this streaming data, if I want to query that aggregation, I would want to write it to a database and query the database, or is there a way inside of Flink SQL to do that?
No, there's not.
Gotcha.
So you cannot do like point lookups in Flink SQL of a materialized table in Flink, or a dynamic, like it's not it's not necessarily a materialized table in Flink. So Flink decides internally whether to materialize something or not. You have to use the resulting stream from your Flink SQL application to get the data you want. So if you which makes sense, because you usually want to build some dashboard or something, and for this dashboard you anyways need all the data in some system. Like you're just, let's say you're just dumping the data into Elasticsearch, and in Elasticsearch you have then a table basically of your cities and counts and averages and whatever, or you're writing it to Postgres, and then you can also build a dashboard or query, like do point lookups of the data.
Of course. And the whole theory architecturally that we covered in the last episode is data comes in, there's computation, data goes out. So this is the data going out, and put it in an appropriate place for that. That
so if
query is doable.
Yeah, so if you're a company that provides a Flink SQL platform, it's pretty easy for somebody to go in and say, "Oh, we have all this data in Kafka, and I want to write it now to S3." And you can do that with Flink SQL. You can define a Kafka table. Basically, you specify this is the topic, this is the broker, this is the latest or earliest offset that I want to start with, and then you can do a select star on this table, which is backed by a Kafka topic. And then you can create another table that is backed by S3. And then you're writing data into this S3 backed table. And depending on how you define this table, it's creating bucket, like it's creating file, like a file per hour, or a file per customer, or a file per region, whatever. Okay. Yes.
We'll put a link. I like how you said that. If you were a company that had a Flink-based data platform, I mean, just for an example, we should put a link in the show notes. If you could send me a link, if Decodable has a good explanation of how that works in Decodable, that would be 100% appropriate to have as a resource in the show notes, because that's going to be useful to some of our listeners.
Yeah, and there's also companies like Uber, for example, and I think also Netflix to some extent, that have built internal stream processing platform based on Apache Flink. So there's talks on YouTube from Flink Forward from these companies, how they build internal streaming platforms with Apache Flink.
All right. We'll get some of those in the show notes too, just for further research. My guest today has been Robert Metzger. Robert, thanks for being a part of the Real-Time Analytics podcast.
Yeah, thanks for having me. It was fun.
And there you have it. If you feel compelled to help us spread the word and grow the real-time analytics community, you can give us a rating on Spotify or Apple Podcasts or wherever fine podcasts are sold. If you're watching us on YouTube, hey, subscribe and, of course, hit that notification bell. And you can always share your favorite episodes on LinkedIn or Twitter or wherever it is you do social media. Thanks, and I look forward to talking to you in the next episode.